Hello and welcome to Data Research Labs. For today's Advanced Excel Quick Trainer, we are going to discuss multiple linear regression. The target audience is students or those working in the science or engineering fields. The objective is to get you up to speed quickly on using Excel's more advanced features, and for best results, put your play speed at 2x or jump to chapters of interest in the timelines below. Sometimes YouTube doesn't have the chapter lines, other times it does, but you can go into the description fields and the chapters will be listed there and you click on the times to jump. First up, what is multiple linear regression? What is multiple linear regression? Well, some definitions. Multiple linear regression, or MLR, is also known as multiple regression. They're interchangeable synonyms, if you will. MLR is a forecasting tool. MLR is a statistical technique using several independent X variables to predict one dependent Y variable. It's much like your simple linear regression, Y equals MX plus B, but it's a bit more complex. You have your one Y-intercept, Y equals B, plus, and then you have lots of MX equivalents, lots of components. And these are your coefficients, B1, B2, B11, B22, and then your X values. And linear regression will calculate all of these coefficients for us so that we can take the equation and plug the X values into it. And finally, the goal of MLR is to model the linear relationships between the independent X variables and the one dependent Y variable. And it frequently is a plane, could be curvilinear, doesn't have to be, but it's not just a simple line, it's going in multiple directions. The multiple linear regression equation is y hat equals b to the 0 plus b1x1 plus b2x2, repeating out to bnxn plus e an error coefficient or value. So what are all these variables? Well, y hat is the dependent variable. That's also known, depending on what industry you're in, as the predicted value, the expected value, the response value, the measured value, etc. But it's typically always known as the dependent variable. B0 is the y-intercept, just like the simple linear regression video that preceded this one. That is the value of y when all of these components are zeroed out because the value of x is 0. X1 is the independent variable number 1. It's also known as the predictor or the explanatory variable, the risk factor if you're in the medical industry, the exposure, etc. An example of these two would be if we were going to do a multiple linear regression model on house prices in a given region. Y hat would be the dollars for the sale price. B naught would be some arbitrary coefficient that the calculation would calculate. B1 would be another weighting for the given independent variable that the linear regression would calculate. But X1 might be the square footage. X2 might be the number of bedrooms. X3 might be the lot size. X4 might be the number of whole bathrooms. X5 might be some premium thing like does it have a garage? One no. So anyway, that is what the X's are. They're factors, independent variables that stand alone, aren't related to each other, but do weigh in and influence the Y hat, the dollar sign, the dollars for the sale price of the house. B1 is a coefficient number 1 for the independent variable number 1, and it's the estimated basically it's the weighting of the independent variable. So some independent variables are weighted higher than others, and this coefficient here will tell us how much more important one is than the other. And there's a principle, I don't think we'll worry about it here in this video, but you typically want to standardize your X values. And so instead of having one X value that's measured in millions and then another X value that's measured in fractions of 1, you want to convert them all to a Z-score. You want to standardize them. You want to convert them all to the number of standard deviations that they are. And if you do that, then all these components are more equally weighted. But anyway, we won't worry about that. Xn and Bn. Basically, this is saying that you repeat these clauses all the way out to however many independent variables that you have. Now, Excel, for its multiple linear regression, is going to limit you to 16 independent variables. But if you use R or Python, you can go out into the hundreds. And finally, the residuals, or error term E, is the difference between the actual Y, say the house sales price that was observed, and the predicted Y in our test data set. If you ran MLR, got this equation, and then you had actual values that you plunked in and calculated to get an expected or predicted Y, and then you compare that to the actual Y, the residuals are the difference between what you expect and what you actually have. And I'll show a diagram on these upcoming slides that show how that's measured. So what would an example of multiple linear regression look like? What are all the components and how does it fit together? Well, at a high level, we have independent variables, xi, so x1, 2, 3, 4, and in this case, these independent variables are going to be used to predict blood pressure, y hat. And this is all just fictitious data plunked in here, it's not real. So if we know that we have x1 body mass index, and we know we have age, and we know I have gender, a dummy variable where male equals 1 and female equals 0, and then hypertension treatment, also a dummy variable where it's yes equals 1 or 0 for no. If we have these 4 independent variables and we have values, if we've previously taken training data and built this model, multiple linear regression model, then we can take new test data, a row of new test data, and run it through the model and arrive at an answer. So in this case, our equation is predict the blood pressure, where our model already has these coefficients B0, B1, B2, B3, B4 already defined, and then we can arrive at our answer. So let's look at what that looks like. Let's see. B0, our y-intercept. We just plunk that value in. B1, our coefficient, negative 0.55 from the MLR analysis that we've done with training data. We just plunk that negative 0.55 in, and then whatever our patient's body mass index is, we plunk that in, 22. And so on. For age, we have the 0.66 regression coefficient, and 49 is the age. And the gender, male, yes, so the 0.92 coefficient times 1. The hypertension treatment or blood pressure medication, yes would be a 1, but it's a 0. This particular patient is not on blood pressure medication, so that whole coefficient is zeroed out. And you run the math, and then you arrive at 88.31 as the predicted blood pressure of this given patient with these given independent variables. Next up, how to activate Analysis ToolPak in Excel. So to get started, if you haven't already, you'll need to activate Analysis ToolPak one time, the first time on your computer, so that it's available in Excel. So to do that, click the File menu, and then click the Options submenu, and then click Add-ins when that pops up, and then select from the Manage drop-down the option Excel Add-ins, and click Go. A dialog will pop up. Make sure that you tick the Analysis ToolPak checkbox, and click OK. And that's it. You don't have to install anymore from Office 365 and probably a few versions earlier, but for sure Office 365. It comes pre-installed. You just have to enable it. Once you've run steps 1 through 5 to enable it, then you can go and verify the data. Menu or toolbar and data analysis option exists. Next up, how to run an MLR analysis in Excel. So how do we run multiple linear regression in Excel? Well, we have to start with data. We have to have an X range of independent variables. That's the values that are going to feed into the equation. So in this case, is this sports car? 1 is yes, 0 is no. How many highway miles were driven? How many city miles were driven? And we have our Y dependent target variable that's being predicted. And in this case, it's not predicted. We have actual values. And it's this set of actual values, an X range and a Y range, that get fed into MLR to derive an equation. Note that in Excel, your X range can have up to 16 variables, 16 X columns. That's it, no more. Limitation of Excel. Next, we would want to click the menu item Data, followed by the Data Analysis button over in the toolbar, and in the drop-down from the pop-up dialog that comes up, select Regression, and then click the OK button. Once the Regression dialog box pops up, we're going to fill that out. The input Y, remember, was one column over on the right. It was F, and it was row 3 to 43, 40 different data points. And then the input X range was 3 columns, C, D, and E. And it was also rows 30 to 43. So I selected those, and we'll see 3 demo examples later, but for now it's a static screenshot. I checked labels because the column headers had label names, so I checked that. I wanted to see a confidence interval, so I checked that. Then I wanted to create a new worksheet. I didn't want to stuff the output ANOVA table. It's a bunch of tables, we'll see in a minute. Plus, it can have many graphs that also get popped up. It's easier just to put it all in a new worksheet. So I use that option as opposed to selecting an output range on the current worksheet. And I certainly don't want a new workbook. And then the 4 residuals, I check them all. Can't hurt. You get a lot of graphs that we're going to go through in a minute. If you leave them unchecked, then you don't get any graphs. So once check them all the first few times you use it, look at the graphs, understand what they are, make a decision on whether or not you need them. And then here's another graph, a normal probability curve. So after we click the OK button at the prior MLR dialog box settings, Excel will calculate for a little bit, and then it'll pop up a new worksheet, and in that worksheet will be output tables, and there's 4 of them. There is a summary output up here. There is an ANOVA section that includes the coefficients for our equation, and we're going to talk about all these in greater detail in the next section. And then there's a residual output table and a probability output table. Now Excel also, in addition to these output tables, will produce output graphs. And there's 3 different styles of graphs. There's residual plots, 1, 2, 3, one for each independent variable, x1, x2, x3. And then so that is one style of report, residual or graph, residual plots. And then there's also line fit plots, 1, 2, 3, x1, sports car, x2, highway miles, x3, city miles. So those 2 reports, and then the third report is a normal probability plot. Next up, how to interpret MLR output tables in Excel. So how do we interpret the MLR output tables? Well, let's start with the first table, the summary output table. And we'll walk through all these different variables that are listed in the regression statistics subcategory. Multiple R is the correlation coefficient. It measures the strength between 2 variables, where -1 is a downward slope, and it's good, means a very strong relationship. And +1 means a strong relationship, positive, going up. And 0 is bad. Slope is 0, flat line, bad. No relationship between the variables. I typically don't use the multiple R correlation coefficient. The R squared, that's the coefficient of determination. That works fantastic for linear regression, but I don't use it for multiple regression. It's an indicator of goodness of fit, where 0 is bad, 1 is great. It's the percent by which a dependent variable, Y variable, its variance is explained by the model, all of the X's and all the different coefficients. But the reason I don't use this in multiple regression is that as you add on additional independent variables, x3, x4, x5, you're artificially getting closer and closer to 1. And if you have 15 variables, it's just going to put you way up close to 1 artificially. So what we actually want to use is the adjusted R squared. That third value is what we want to use for multiple regression to determine the goodness of fit. And the closer the value is to 1, the better the fit. And actually, if it's less than 0.85 or 0.80, probably not a good fit. If it's down to 0.65, 0.5, that's a terrible fit. 0 would be just a random cloud of data, no relationship at all. And the standard of error, the 4th row here, that indicates the goodness of fit as an average distance that the data points miss the regression line, or how wrong is the model on average. So the predicted Y value, how far off is the actual value from the predicted value from the actual value. I don't really use that, but if it's way off, then you know, ooh, not good. And then observations, there's 40 observations. I don't really use that either. Really, in this summary chart, the value I use the most is the adjusted R squared. Next up, after the summary output table, is the ANOVA output table. And there are 3 rows, regression, residual, total, and there's 2, 4, 5 different columns. DF is degrees of freedom, sum of squares, mean of squares, F statistics, significance of F, and we're going to walk through each of these. The degrees of freedom is associated with the sources of variance. So we know we have 40 data points, minus 1 is your total. So the total is always the number of observations minus 1. That's our 39. And then we have 3 x variables, or independent variables. 39 minus 3 is 36. Next up is the sum of squares, SS, and there's a mean of squares. Before we get into that, what's going on is your red line is the predicted value based on the equation that we set up, and the blue dots are the actual values, and the green lines here, that's the residual. We're measuring the actual point minus the predicted point, and that gives us our delta. The delta is the error, which is also known as the residual. All the same thing. Delta, error, residual. All the same thing. Green line. So we're taking these green lines and we're either summing all of them or we're taking the mean of all of them. That's what's going on visually. So when we look at the sum of squares column here, what we're looking for to be good behavior is the residual, the error. We want that to be small relative to the total. And so that's what? 309 into 659, so it's like a half. But the smaller this is relative, the residual is to the total, the better. Let's move along to the mean squares. And the mean squares here is just the mean of the green lines. And this pictorially is just linear regression, but we're actually doing multiple linear regression, so there's multiple dimensions of these red lines. So we're just taking one x variable and looking at it, but think of it as a plane and it's going on in multiple directions. Anyway, the mean squares using the F statistic. How? Well, if you look at it, the F statistic really is the residual, the error, 8.5, goes into the regression, the actual squares. 8 times 2,500 equals 21,800. So that's how the F statistic is calculated. It takes the regression mean square divided by the residual mean square. It gives you the F statistic. And why don't we just jump down there? And so the F statistic, or F test, is for null hypothesis, and it's used to measure the overall significance of a model. And a higher F is good. And again, it's the ratio of the regression of the MS divided by the residual MS. And so 2,000 is great. If you had 1, if you had 21,000 for your residual error relative to 21,800 for your regression, then your F statistic would be almost 1. Or if they're equal, it would be 1. And if you have 1, that's a bad F statistic. So anyway, small F statistic towards 1 is bad, high F statistic is great. And that's the reasoning why. Because you're measuring basically the average of these green errors, and you want that average to be small relative to the size. So this regression here is basically measuring the red line down to the height of the red line down to the zero intercept. Well, actually, the zero intercept is right there. That blue line is off. It should be up a little bit. Anyway, the significance here, move on to that. The significance of F, that's basically the p-value of F, and it's the probability of attaining the results at least as extreme as the observed result. So if that significance of F is less than 5%, then the model's good. And look at this, e to the negative 42, that is a lot of zeros before the 5. So that's a highly accurate model, whatever this test data was that I used to run through here. So that is the ANOVA table and all of the different components. Now we move along to the third table in the MLR output table section, and it's the equation coefficients, and it sits right below the ANOVA table. And here's our coefficients. They don't come colored. I color coordinated them so you could see red matches to red, green matches to green. I'll explain that in a minute. But these coefficients are the most important column of this table, I think, and they're used to write the formula for predictions. And I'm going to go back and describe it now. So when it says intercept at negative 1.9, in our y equals b0, that's our intercept. There's no x component. So that b0 is the negative 1.914 right there. These three are x1, x2, x3. There are independent variables, are predictor variables, and is sports car, b1, we plug it in there. The is sports car, that's an x value that we would plunk into our equation when we're done. So basically, we're taking this equation coefficients table from the MLR output, and we're generating the predictive model from that. Y equals negative 1.914 plus 7.35 blah 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 times is sports car x value plus 1.15 blah 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 times highway miles plus 0.395 blah 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 city miles. So that's how that works. That's an important table so that you can generate your predictive model. And once you have this predictive model built from your training data, your X's and Y's earlier in the video. From that point forward, you can use this model to predict future values. So 6 months later, you can pull out this equation, plunk in, is it a sports car? Yes. How many highway miles am I going to drive? 50. How many city miles am I going to drive? 5. Run the calculation, and you'll have a predicted time, how long it's going to take to do the drive based on your historical MLR linear model, multiple linear regression model. So very useful table. The next column is the standard error column. It is an estimated standard deviation of the least squares estimate. I don't really use it. The next column is the t-statistic. Computes the t-statistic for H0, H0 versus HA, your null hypothesis versus your alternate hypothesis. I'm not going to discuss that, but it's there. The p-value, that's important. Typical in all scientific measurements, 5% error. So it measures whether the dependent variable is statistically significant, and we want it to be there's less than a 5% chance it's due to random noise. So if it's less than 0.05, we reject the null hypothesis, and then we can say that, oh yeah, like to the X1 component, independent variable is sports car, has 1.9 to the negative 0.7. That's well below 0.5, and this one's well below 0.5. So these two are solid, these two independent variables. This one here at 10%, fine, I'd accept it, but ideally it'd be less than 0.05. When I built up the test data, I probably didn't do a good job, and and that's why that's not less than 5. And then this intercept, I'm ignoring that at 16%. It's not like you would just remove the intercept. Whereas these other variables, if I had 12 or 13 variables, I'd look at that p-value. If there's a p-value that was far off, or there's a coefficient that was tiny, you know, the most important, well, it depends. I didn't standardize the data. But theoretically, the most important, you look at a combination of things. You look at the size of the coefficient. It's kind of the surrogate for the weighting of how important is this X variable in the overall flow of things. But you also look at the standard error. So that's a big standard error relative to these two. So even though 7.3 is much bigger than 1.1, its error is even bigger. So the blue is the green is 7 times bigger than the blue, roughly, as far as coefficient size. But standard error, it's way bigger. It's 100 times bigger. So this is, anyway, the highway miles is, I'm getting off track. But the p-value, you look at those and you would make a determination. If it's really bad, you might throw out one of the variables. And lower 95, upper 95, that's a confidence interval for the given coefficient. And it's the likelihood. It says that there's a 95% confidence that the coefficient value given actually falls between those ranges. And moving on to the fourth table, the residual output table. Well, I guess it's the third, because these two are tied together as 2, and this is the third table, residual output. And we have basically the number of the observation number 1 through 40, each data point plotted, and then we have the predicted Y is the predicted trip time. That's our calculated value, and it's the predicted, so it's the Y value after we plunk it into the equation, and we're going to compare that through the residual to the actual time. So 118 is the predicted, 122-ish would have been the actual, so it's -3. And then it's the actual minus predicted for each data point, the residuals. And then the standardized residuals, this is important. So the raw data is 118.65 minutes, and the residual is that. Well, the standardized residual says, look at all the residuals in all 42 measurements taken, or 40 measurements taken. Yeah, 40 measurements taken, observations. Look at all 40 and standardize them. And then this tells me that it's like a z-score, and it's important for weighting your coefficients. And so it says that, or not your coefficients, weighting your observed rates. It's instead of my error residual is -3.35 minutes, it's saying my error residual is -1.19 standard deviations. And so it just standardizes everything. And finally, we come to the probability output table in the lower right, and that's the percent of cases whose trip time, or Y value, is predicted to fall at or below the given value in the chart. So it's like a percentile ranking. don't have enough shown here, but it's saying that 3.75% of all observations fall below a trip time of 5.3. So this number goes up to 100%, and this number goes up to whatever the maximum observed rate is. And these are raw numbers in minutes, or whatever my Y value that I'm predicting happens to be. That's just the nature of my given data. So probability output, it's used in one of the charts that we're going to see how to interpret later. Next up, how to interpret MLR output graphs in Excel. So the first MLR output graph that we're going to learn to interpret is the residual plots. And there's, in my example, 3 of them. But there's one graph residual plot per independent variable. So X1 is sports car, one independent variable. X2, highway miles. X3, city miles. That's my 3 independent variables. And there's one graph per. It depicts the actual versus predicted residuals or errors. And so, like in this case, the predicted value is on our 0 x-axis here, and our error values, our actual values here, and the distance between the line and the dot is our error. That is the residual that we're calculating. The residual plot is showing that. Now, what good is residual plot? This one is just tough to make out because the value is either 0, it's not a sports car, or 1, it is a sports car, and all the values are clustered on those 2 x values. And so you can't do that much analysis with it other than to say that, yeah, they're equally distributed above and below. Here they're clustered a little bit lower, but you do have values above and values below, so it's okay. Here, yeah, there's some above, some below. It's not too bad. But my $50 graduate school statistics class, homoscedastic. The residual plot should be homoscedastic. And what that means is there should be an oval, and all the dots should be randomly distributed within that oval. There's a gap here. That's not ideal. It's probably because I didn't do a good job of creating the test data for this. But it is pretty random. You have some dots above, some dots below. They're randomly all over the place. I only took 40 observations. If I had 200 observations, it would fill out nicer. And you should not see any pattern. You should see roughly as many dots above as below. The next MLR output graph is the line fit plots, and they're close relative to the residual plots. There's one graph per independent variable. X1 is sports car, one graph a line fit plot. X2, highway miles, one line fit plot. And X3, city miles, one line fit plot. These graphs depict the actual versus predicted Y values. So the orange dots are the Y values, and the blue dots are the actual values. Unfortunately, this is a screenshot image pulled over into PowerPoint. I don't want to take the time to go back into Excel. I should have made the orange dots transparent so you could see all the blue dots underneath, and you could see the variance better. I just didn't realize it until now, unfortunately. But what's going on is over here, see how there's wider swings? The residual, the difference between the predicted and actual is wider here. It's further away from the 0, and this is further away from the 0, and you see that right here too. Right before 100, right at about 90, 80, and what do you see right here? Right about 90, 80, you see the blue swinging wilder on both sides. So really, this is just a view of the deltas off of the line. So if the orange wasn't here, you would see a predicted line, and then the orange is supposed to, it's the predicted values. Anyway, that is what this is showing. It's the raw data behind the residuals over to the left. And finally, the third MLR output graph is the normal probability plot here. There's one graph per run. Doesn't matter how many independent X variables there are. And it should be a straight line, or relatively straight line, that goes up to 100 because it's 100 percentile. Shouldn't have that. I just let it auto scale. And the straight line would indicate that there's a normal distribution of the data underneath, and that's what you're looking for. You don't want any skews to it. Next up, example number 1, a trip time model. So now we're going to demo example number 1, where I have some of the test data we were seeing earlier in the video with a vehicle type, 3 independent variables. Is it a sports car, the highway miles traveled, the city miles traveled, and then I have a Y value, which is the trip time in minutes that we're trying to predict. And in this case, this is all our training data, so we have actual values for the 3 independent and the 1 dependent variable. And since we have all the values, we can train a model and derive the model. So that's what we're going to do. So we're going to start out after we've got the data and we've identified it and we've made sure that x1, x2, x3 are all adjacent, contiguous data. You can't have a gap. You can't have a column in here. If I have a column with some other stuff in here, then it won't work, the MLR regression model. You can't select this range and then hold down the control key and select this range. You can't do that with MLR. They have to be contiguous. So that's important to note. Well, let's go ahead and get started with the demo. So we're going to go to the data menu item, and on the toolbar over here is data analysis. We will click that, and we want regression, and click OK, and up comes a dialog box. And now we're going to make some choices. I'm going to cheat and just go down here and go check, 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 check. I'm going to check everything. And the new worksheet, I'm just going to fill that out. I'm going to call that run number 1. I want it to go to a new worksheet. I don't want to output a range on this sheet, and I certainly don't want a new workbook. I'm not going to do a confidence level. It has 95 by default, and I could check it and do different things. I'm just leaving it alone. I'm not going to do constant is 0. I am, however, so when I select the Y range here and I select the 3X ranges, I don't want to just select the data and then have no name. So I want to select the labels, the column headers. So let's get started. Let's do the input Y range after checking that. Click in here, click here. The dialog disappears because it's in select mode. Click here, Control, Shift, down arrow. Got the whole range, all 40 rows. Hit this little guy to return to the dialog. There we go, F3 to F43. One column, 40 rows. Now let's do the input X range. I don't just have one X, I have multiple. So I'm going to click in here, hold the Shift key down, get the column headers. I took my hands off the keyboard. Now I'm going to hit Control, Shift, and down to jump to the end. 3 columns, all rows. C3 to E43. Looks good. Looks like I have everything. Hit OK. It's going to whirl, whirl, bam, done. That's run number 1. I don't like all those grid lines, so fine. I'm going to select the entire cell range and change to white, make it look like a sheet of paper. I'm going to select all of this range and double click it so that the columns are readable. Bring that one back in, bring this one back a little bit. So there we go. There's my summary output, my regression statistics, my adjusted, look at that, 0.99. That is a really good adjusted R-squared value. ANOVA, 8, yeah. So that's a high F value is good. It's not low. If it's 1, it's terrible, because then the number of errors residual is as the mean square of errors is as big as the mean square of the actual data points in the regression. So we would not want this over this to be close to 1. It's not. It's big. And then the significance. That's great. It's a tiny number. Think of it as our p-value, and it's way less than 0.05. That would be 5 to the negative 2. And this is 5 to the negative 42. So excellent. And our intercept. This is our equation. So if we were to pull this out, it'd be y equals minus 1.91, blah, 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 plus 7.34 times x1, plus, and so on. And our standard errors, that's good. I'm not going to look at t-statistic. Those 2 are excellent. That one's that one's 10%. I mean, we'd like it to be less than 5%. And then these are our confidence intervals. And because I didn't enter any, it just defaulted the same thing twice, so ignore that. And our residual output and our probability output. This gives you a better view of the probability output. Percentile all the way up to 100 should be, yep, 98. Because the last 1.25% that gets us up to 100 is included in this bucket. So 98.75 and greater % of the data points. And it's because we have 40 data points. We have less than 100 data points. So 40 goes into 100. That's probably our 1.25. Anyway, doesn't matter. That is our tables. And what else do we want to look at? Yeah, why don't we write out that equation so we have it demoed at least once. So let's do equals that value Well, I don't want that though. If I do a formula, that's fine and dynamic, but I don't want that because I'm going to copy paste the formula. So equals, how about this? I will copy and I will temporarily paste the value, and that way I can copy that whole thing. There we go, copy. And so the function is going to be equals that value plus, well, let me hit enter. Actually, it's more convoluted than that, so why don't I grab these values. Actually, oops, why don't I even make it even clearer? I'll do an I there, and I'll do an X1 here, and an X2, and an X3, and I will right justify these, and I'm only going to do this for this example. I won't repeat it for the next two examples. I will go back to my example 1, and I'll paste my values just in the table over here. The column header's making it off. When I go down, there we go, paste it right there. There, that looks better. So my formula is going to be equals that value, and I might as well click F4 on it because I want it to have the $sign so that as I copy the formula down, it's not going to shift down here. I want it to always stay on that function. Anyway, equals that plus this coefficient times this X1 plus this coefficient times X2 plus our third coefficient times our third X value. We should get somewhere close to 115. We do, we get 118. And now if I take and copy that, left, control down, right, control shift up, control V to paste. Well, what did I get wrong here? Huh. Oh, I know exactly what I got wrong. I did the $signs there, but I missed them here, F4, and here, F4. Oh, wait a second. Undo, 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 undo. Okay, escape. Okay, that B component for our coefficient, I want to be fixed over here. But our C, D, and E, I don't want to change. So Q, your locked in absolute value. C, your relative value. Q, anything that's a Q needs to be absolute value. There we go. Now when I copy it down, it's not going to shift off of these. Control shift down, Control V. There we go. And so that's my actual value. That is my predicted value. And actually, insert, if I wanted to manually calculate my residual, and we were talking about residuals in a lot of these, it would just be the actual value minus the predicted value. And that's where our -3 came, if you'll remember back a couple of slides. And I could calculate the residual for all of these. And they should all be relatively small, plus or minus above or below the actual value. 111, yeah, oh, really? Oh, I understand. I was wondering why it was off. It's rounding. That's not 111. If I make this wider, it's 110.6. I look at the math going, that doesn't compute. Well, it's just rounding. And I think that wraps it up for this particular example. Next up, example number 2, a house price model. So for example number 2, the house price model, I found on Kaggle.com a data set. The URL is right here, and it's too big to state out loud. So I'll copy paste this into the description down below in the YouTube video, and you'll have to expand the see more, and then you'll see the link and you'll be able to click it. So in this data set from Kaggle, there are 81, actually go down here, there we go, 81 columns. They have such a rich data source here. They have everything. Does the house have a fence? Is there a miscellaneous feature? Is there a miscellaneous value? What month was it sold? What year was it sold? Etc. They have a lot of independent variables, 81, and columns. And Excel can only handle 16, and I didn't even want to use all 16. So I took a guess. We're going to predict sales price, Y. Lot area is important, building type, important, and there's codes for these if I hover. Let's see, 1 family, 2 family, 3 is a duplex, 4 is a townhouse, etc. The overall condition, 1 to 10. The year, anything that's numeric is fine. I can leave it as is. Anything that was like this, like neighborhood, that's a bummer. I should have put neighborhood in, but I just wanted to get this done faster for the presentation, so I did not encode all of these 15 or so values into a numeric value, which I should have done, because I think having neighborhood as an independent variable would have made the model more accurate. But anyway, I had to pick some, so I picked these 8 variables. I left others out, therefore my model's not as accurate, but that's what we're looking at. There's our test data. 1 to 1,460 sales, and these independent variables here, 8 of them. And that's what we're going to use in our linear regression model. So let's see, building type. Yeah, I talked about that. I had to convert the building type over to numeric. So let's get started. Let's go to data and data analysis. And regression is remembered from the last time I ran it, because I haven't closed Excel. Hit OK. These are the prior settings. They're all wrong. I do want all of these graphs checked because I want to include all those graphs. And I do want a new worksheet. I don't want it to go to run 1. I'll have it go to run 2 because this is example 2. And I'm going to include the labels. But the Y and X values, let's just clear them out right now. And then let's go reset them. So what's my Y value going to be? Well, I know it's going to be, and I'm going to include the column header sale price. Control Shift down. Yep, 1462. 2 rows are header. 2 to 1462. And then our X range, and this is kind of fun because just drag the thumb all the way to the top. I'm going to click here, and look at that, we have 8. There we go, 8 columns. Oops, I did that wrong. Let me go down to the blue column headers. I want the variable name, not X1, X2. So there we go. I have X1 through X8 selected, and then Control Shift down to get all the data. And yep, C2 to J1462, row 2 to row 1462, column C to column J. Looks good. I'm going to hit OK, and it's going to crunch the numbers. I'll just pause the video. I didn't have to pause it. It was just about 5 seconds later it was done. But there we go. There's our model. So I'm going to do like I did last time and highlight, click the little corner here, highlight all the cells and flip them to white. I like that trick. Matt Winberry taught me that years ago. If you ever watches this, Matt Winberry, that was you that showed me this. Highlight all the columns, double click. Yeah, it's a bit wide. That's a bit wide. And I'll leave the rest of them. Okay, so let's go do some analysis on what happened here. Summary output, our first table. We don't pay attention to these two, but the adjusted R-square is important. See, it's 0.62. We really want it well above 0.8, 0.85. We want it in the 0.9, 0.95, 0.96 range. That's not good. So I did a poor choice in choosing the independent variables when I chose these 8 out of the 81. There were probably a few better ones. Lot area is important. The general living area, that's important. I got that. The number of bedrooms. Yes, I don't have the number of bedrooms, for example. I have full and half baths, but not number of bedrooms. And there's some other important criteria that I excluded, and you can tell because that's not a very good linear regression model with an adjusted R-square of 0.62. So that gets I don't like red. I'll lighten up the red here, like a salmon color. So not good. The ANOVA F here. Yeah, the ANOVA's fairly big, but it'd be better if it were in the thousands. So it's okay. Give it a light green. The significance, e to the negative 303. Wow, that is tiny. That's really good. And this is fun. This is all our coefficients, so we could make one heck of a big equation. Y equals negative 240, no, that 2.429 million, blah, 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 plus 0.709, blah, 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 times x to the 1 plus, or it'd actually be a minus. So anyway, we'd plug all these into our formula, and we'd have a formula for predicting the house price based upon the lot area, the building type, the overall condition, etc., etc. Let's see, prediction equation, the p-values. Okay, so let's look at the p-values. negative 62, negative 07. These are all tiny p-values. Even that one is to the negative 4. 1, 2, 3, 4. That's great. That one is much smaller than 5%. It's 0.7%. Uh-oh. That's a bad one. The half bath, I should toss that. So that one right there is, that's not a good. That's 70. Wait a second. P-value 45. It's 45% chance. I mean, random white noise is probably flipping this around. So I should not have included this as an independent variable with a p-value that high. But the rest of the p-values are all really good. Even that one's great. They're all a pass. And then I would probably toss this and go pick one or two others. And you iterate on these independent variables with your model, and you try and dial your model in, and you try and try again. And eventually, you never use all 81 variables. That's too many. And are all 81 of them significant? No. Probably only 8 or 9 or 10 of them are really that important. And so I just have to pick the right 8 or 9 or 10 independent variables here from all these grayed out ones that I ignored. I mean, if we go eyeball it, year built's probably important, but I did have year of update. So the remodel, they both move in the same direction, so it's good to pick one, not both. You don't want to have multiple independent variables that interact with each other, and year built and year updated would interact heavily, so the one I picked was good. Siding, type. I'm sure there, house style. I didn't include that. That's probably a good one to include. Anyway, that is what we would do with these coefficients and how we would iterate over and over until we got a good model with a high adjusted R-squared, plug in the values and go from there. Residual output, I'm not going to talk about these two. I can go look at these graphs, but they're kind of hard to read. So maybe what I'll do is just, geez, there we go. Look at that. So there's one normal probability plot regardless of how many independent variable x's that you select. This should be a straight line. The fact that it's not, kind of like salary, house prices, they all swing a bunch. And so instead of being a straight line, the percentages, it's like an S-curve. They go up, they flatten out, and then they go up again, and they really spike at the end. So it's not a normal curve. And that's probably what's throwing my model off, is this tail end here. So I could go chop the model here and limit the model to inputs below $400,000 sales price, $380,000, and then we'd have a nice linear model that ends at $300,000, and the R value would go way up. The fact that it curves, if I were doing simple linear regression, I would just go change it to a curved line, and it's harder, more difficult. I'm not going to demo that here and go figure that out. But anyway, that's what's going on, is that curve is throwing our linear line off. How do you fit a line to that? Probably by shooting the line straight through something like this, and you're going to have a big error in here and then a bit of error up there, and that's why we get 62%. So anyway, just looking at the graphs, you can tell that kind of information. And looking at the graphs, you can say, you know what, let's clip our model at $400,000 and less, and then we'll have a much more accurate model. And then maybe do a separate model on a steeper line that predicts above 400,000. So that's what that graph can tell us, but that's the actual line fits. For total rooms above ground, I'll just delete it. And half bath, 0, 1, 2. Wow, no houses had 3, but some had 2 half baths. Must have been big houses. Full bath, 1, 2. Some had 3 full baths. General living area. Now that's a nice scatter plot because your square footage is all over the map. It's not in fixed positions of 1 or 2 or 5 buckets. You have nice granularity there, and sales price is the same, so you get a nice, pretty scatter plot. Look at that, interesting. The blue actual sales price is kind of, it's a lot, some of it goes up and some of it goes this way, and the predicted shoots right down the middle, and there's our error. You can see the error, the blues that are off of the orange, the actuals that don't match what we're predicting. And the interesting year remodel, 1950s up to 2000 something. They're all clustered. Interesting. I've never looked at this data. It's interesting to see it spike in the 1950s and flatten back down, And then in the there you go, 1970s, flattens back down, then it spikes again. What is that? Hover, 1996, and then it flattens back down. And the data only goes out to 2007, right before the market crash, and then it flattened out, and then it started to pick up again 10 years later. Interesting. You can see those blips in there. Another line fit plot. Lots of line fit plots, which is raw data, actual versus predicted. What does this tell us? Lot area. Interesting. The bigger lots don't necessarily sell for more. A little bit more, but they kind of curve off the lot size. I'm sure location matters much more. It has a view and other factors like that in the neighborhood. And now we've moved to residual plots. There's no more oranges. So this is telling us what was the difference between the orange and blue dots on the last graph. Whatever the distance is what we're measuring here. And look at this. This is not homoscedastic. The residual plot gets wider and wider and wider as you get out. So that's bad. So we have an issue going on there that we should take into account. And I'm not going to deal with that. I'm not going to deal with that. Let me scroll. I'm taking too long to describe this. I'm just going to go through it really quick. What do we have here? The general living area and the residuals. That's not too bad. That is, wow, look at all that cluster in there. There's some outliers, but whatever. In general, you kind of have a disc shape. It does do more of a cone shape, so there's a little bit of a problem going on there too. There we go. This one's nicer. It still flares out at the end like a trumpet, so all of these have a little bit of an issue. And finally, example number 3, multivariate chemometrics in heroin profiling. So for example number 3, the heroin profiling model, I went and did some Google searching looking for a good multivariate chemometrics data set and found one, and it's at the NIH, National Institute of Health, Government, US, and it's got a Creative Commons license if you browse through to it. Okay, so for example number 3, we have downloaded the data from the National Institute of Health. It is the heroin data set, and it consists of 38 heroin samples that were seized from different locations in Serbia. And the data is a subset of that posted by, thank you, Aran J. Parm, Res in the autumn of 2016. And I've given the links there, and also in the prior slide I gave the links, and I have the data set URL down in the description on YouTube, so you can get back to that data set. And the data set says that it's Creative Commons license as well. But it's a nice data set. Now they have 3 different locations. This is one location with 4 different chemical signatures in the heroin that it's looking at. And I don't understand all the details of the actual drugs. I'll look at that in a moment, but it's doing some kind of signature let's just go down and read it so that I don't mess up the name. Anyway, this is one set of data, and then there was a second and a third, and I got rid of those. For the purpose of this test, I only wanted to look at one. And so the objective of this example is to use multiple linear regression to facilitate forensic profiling and chemical analysis of illicit drug samples. And they want to determine the origin, the methods of production, etc. So basically you would look at the ratios of these chemical compounds within the illegal drug, the heroin, and based upon the ratios you could tell, oh, it came from here, it came from there, etc. That's the theory anyway. And that's, if you go to the article, it's pretty impressive. They go through and do it for 3 different samples and compare things. Pretty neat. But we're just going to do the one model. DAM, DAM is diacetyl, I don't even know how to pronounce it. Morphine, it's the main psychoactive component in all of the drugs. Shouldn't say variables, but it is in all the variables. /DAM, 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 and then there's different related chemicals with it. And Y there is what we're predicting, and then there's the dependent variable, and then here's the independent variables, the predictor variables. So if you measure these 3, you can calculate this one. And TEB as well, whatever. There's all the chemical compounds. I don't know what they are. I'm not going to pretend to know what they are. But we're going to run an MLR analysis on it, and we're going to use these Y's and X's. So let's just jump into it and see what we get. So we're going to go to Data and Data Analysis and Regression. I've had Excel open for the last couple of examples, so it remembers that I use this model last. If I closed Excel, it might forget, and I'd have to scroll and find it. Hit OK. I like to have the labels. I include them when I select the Y and X ranges. And I check all of the graphs to be generated down here. And I want a new worksheet, but I want it to be run number 3 because this is example number 3. And lastly, I could just select, I'm going to just highlight it and delete it so I know I'm starting fresh. Okay, so let's go to the Y range. And I know that that's my Y range, and I want the column header, the name of the Y variable. So Control Shift down, got it. 2 to 40, column J, yep. And then our X range, this, scroll back up, Shift, right, and then Control Shift down. There, got it all. K to M, KLM, 3 columns, 2 to 40, those rows. I have everything I need set up, so I'm going to hit OK. I'm going to wait, small data set, bam, run number 3 is generated. Highlight all these, double click because I want to be able to read it. Highlight the entire sheet, go back to home, flip the back color to white. There, now it looks like a piece of paper. And let's do some analysis. Adjusted R squared, oh, fantastic, 99.99. That data that they have, it's excellent. So the fit of our model to predict Y, the DEB/DAM, based on these 3 X's is really, really accurate. 99.92% accuracy on the fit. 38 observations. Oh, what do we want to look at here? We want to look at a high F. High F is good because that means we have a low residual mean square error. Very low error relative to the regression line. We're measuring small amounts. These are small amounts, and since they're so small, when we sum up the means, it's not going to add to much, and we don't have that many samples. So the means are going to be very small, less than 1, around 1, and then the mean when you have 38. Anyway, so big F is good. Significance of F is tiny. That's good. If this were high, above 5%, if it was 10, 15, 20%, that would mean that the accuracy of this F statistic isn't accurate. But this being very low means that this is very accurate, and this being very high means that the residuals we're measuring aren't that big. So it's like an error of an error. Okay, what do we want to look at down here? Just the coefficients. The intercept is tiny. Y equals negative 0.041, blah, 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 plus 0.379, blah, 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 times x1, which is this component right there, and then x2 is that component, x3 is that component. We could do our equation from that, and we could plunk the numbers in. I'm not going to do that. We've done it before. And let's go look at our graphs. There's so many of them generated. Oh, that's interesting. That's not good, but our normal probability plot, it should be a straight line. And how high is this? 88 is my x value. I want my y value, which is 0.07. That is so tiny. How about the rest of these? 0.027. It's because our values are starting out so small that wow. So what it's saying is that 88% of our data falls below 0.07 on the TEB dam. Let's go look at that. TEB dam, yeah, they're all, yep. There's our 2 big ones. They're giant, and a third big one. And if we go back to our graph, there's going to be 4 big ones to get us up to 100%. And then 88% of them are tiny. So, interesting. Those just stick out like a sore thumb. Interesting. And what else can we tell? Let's get rid of this and walk through some of the other graphs. Usually I'd restructure these and align all the graphs to make them pretty, but for this demo I'm not. Line fit plot. Oh, look at that. The oranges are always on top of the blues. So that's why we're at 99.9 on the adjusted R squared, because the difference between the blue and the orange dots is nothing. So that's a good fit. Same thing, blue and orange delta, nothing. Blue and orange delta, nothing. Now we've switched to residual plots. We only had 3 variables, independent variables. Not bad. I mean, there's not that many points, but it's kind of a disk, or kind of randomly associated. Oh, those ones aren't. They're all clustered there with a few. There's our 4 outliers. So this PAP/DAM is what's throwing it off. PAP/DAM. Yeah, 0.44, 0.47, an order of magnitude above all the rest of the rows that have a 0.0 something. So these are throwing it off. That's what we're seeing here. These 4 values, everything else clustered. There's 2 of the 4, it's part of the same, and then there's 2 more down there. And we're going to see the same thing on the next graph. We're going to see clustering low, and then we're going to see high. And actually it's going to be even more extreme, so let's go look. Yeah. So there's 2 there and 2 there, 4 total. I see 2 because they're on top of each other, but they're way extreme. Over here at 7, and everything else is clustered. Interesting. I wonder why those stand out. Someone who knows chemistry, my sister probably would look at that and go, oh, that's telling us something about that particular drug, but I know nothing about these chemicals or drugs. I just know that the data is pretty cool, and when we plot it, the linear regression line has a nice, accurate model generated from it. And I think that wraps it up for this whole presentation. I wanted to run through those 3 models and show how you hook the data up into the MLR model, and then you get your run results and how you interpret those run results. So thank you for watching. Thank you for watching, and please, if you found this video helpful, click like and be sure to subscribe below. Also be sure to check out our related videos in the boxes to the left.